Let's take a look at the last case where the lines intersect, sorry, the planes intersect in a line. So keep in mind what we want to find when we solve this system of equations. The result should be a line equation. So we want something that looks like the equation of a line in three-dimensional space. Proceed by the same method. So I label each equation 1 and 2. If I take a look at these two equations, I could begin with elimination on the x variable. But notice that the y variable, if I actually added the equations, I have negative y and positive y. So I could add the two equations together and it would eliminate y. So let's do that. We don't have to do any multiplying by equations. So I'm just going to add 1 plus 2. And I'll end up with 3x plus 0y plus 2z minus 7 equals 0. So I just added the x's, minus y plus y is 0y, z plus z is 2z, and minus 1 plus minus 6 is minus 7. And that's all we can do. We've eliminated x, and we end up with this equation with two variables. So 3x plus 2z minus 7 equals 0. And because the y variable has actually been eliminated, it's gone now, at this stage I actually would like to continue and actually figure out what one of these variables is equal to. If I could solve for either x or z, then I could go back and substitute in the previous equations to actually find the intersections. So the y variable has been eliminated, and as I said, we would like to continue and actually solve now for x or z. So what we do is we actually, it seems like we're kind of cheating in a way. If I knew what z was equal to, I could substitute in a value for z here and then solve for x. And then I would know what x and z are, and then I could go back to one of the original equations and substitute for x and z and then solve for y. That's what we call back substitution. So once you've found one of the variables at the end of elimination, you work backwards and actually substitute to find the previous variables. So what we do here is it seems like kind of a cheating thing. We say z is equal to some number, but we know we're going to have an infinite number of solutions to this system. So we're going to let z equal t. So it seems kind of strange because z looks like a variable and t looks like a variable. Z is really any number, and t is actually some particular number, some particular z value. And this is what we call a parameter. And you've seen that before. We've used it for equations of lines, but we've also used it in the past when we've solved different things, where we let a variable equal a parameter because it's some specific number. And so now that I can say, well, I've actually found what z is. It's actually equal to this parameter t. And I know there's an infinite choices for t, an infinite number of choices for t, but I've actually found the variable z. And now I can do back substitution. So if z is equal to t, I can sub z equal t in to 3x plus 2z minus 7 equals 0. So I get 3x plus 2t minus 7 equals 0. And then rearranging this for x, I get 3x equals minus 2t plus 7, or x is equal to minus 2/3 t plus 7/3. So we've actually found the variable z. It's in terms of this parameter. And we found the variable x in terms of the parameter. The last step is to actually find the y variable in terms of the parameter, and for that we have to go back to one of the original equations. So we could use either equation 1 or equation 2. Equation 2 has coefficients of 1 on each variable, so let's use that. Let's use that one. So we're going to substitute x equals minus 2/3 t plus 7/3, and z is just equal to t. We're going to sub that into equation 2. So I get minus 2/3 t plus 7/3. That's the x variable. Y variable, that's the one that we're trying to find, and then z is equal to t minus 6 is equal to 0. So now I can rearrange this equation and isolate the variable y. So I end up with y is equal to 2/3 t minus 7/3 minus t minus 6. And so y is equal to negative 1/3 t. So just combining the t terms, and then combining the constant terms, I have minus 7/3 minus 6, which is minus 18/3, so I get minus 25/3, or 25 over 3. And so that's my third variable. Now it might not feel satisfying that we've solved the system of equations. We found x, y, and z, but in terms of this parameter. But remember that we wanted to find an infinite number of intersection points, because the intersection between two planes is a line. And we've actually found the equation of a line here. It may not look like it at first, but it's actually the parametric equations of the line. And so let's just bring these together in our conclusion. So therefore the intersection line of the two planes is x equal to minus 2/3 t plus 7/3 y is equal to minus 1/3 t minus 25/3, and z is equal to t. So this is a line, and these are the parametric equations of the line. So just to recap, fairly long video that went through using elimination to solve a system of equations. So we're solving a system of two equations with three unknowns, and we did that for each case of two planes in three-dimensional space. We found no solution when we solved, or we had two planes that were parallel and distinct, and an infinite number of solutions where the planes were parallel and coincident, and the infinite number of solutions was just one of the plane equations. And then finally we did the intersection of two non-parallel planes and the intersection in the line. This one took a little bit more work. We used a parameter to replace one of the variables, and then we back substituted after our elimination to find the other variables x and y in terms of the parameter, and that gave us the result of parametric equations of a line in 3D space as the intersection line of the two planes.